Hello, hello. Hey guys, I hope all of you are doing well. So I welcome you all to yet another video in the Databricks playlist, and in this particular video we are going to talk about schema evolution in Databricks. So we are going to understand what exactly schema evolution is and how we can handle schema evolutions in our Databricks workspace. So there are different ways in which we can handle the schema evolution, and we will understand each of them. So in this particular playlist of Databricks, we have covered Spark from the very basics, like we have covered concepts like how we can add a new column, how we can rename a column, how we can do sorting, merge operations, and all these things. As well as we have also covered the advanced concepts like the join operations, group by operations, creating UDFs, handling null values, working with JSON file formats, and much more. So if you are someone who is trying to learn Spark from the scratch or someone who only wants to cover the advanced concepts, this particular playlist can be helpful for you all. So with that said, let's get started with this particular video and let's get straight into the system. So here you can see that the topic or the documentation that we will be going ahead with will be the schema evolution in Databricks. So what schema evolution refers to a system's ability to adapt to change in the structure of data over time. Okay, so evolution means change. So schema evolutions means the schema of the data that we will be having, it can change with the time, and the ability of our system, or I would say of our pipeline, is what is referred to as schema evolution. That it's if with the time the schema of my data changes, right? So how my table or how my I would say pipeline will react. Will it fail? Will it be able to adapt to the change or what? So this is what schema evolution is. These changes are common when working with semi-structured data, event streams, or third-party sources where new fields are added, data type shifts, or nested structures evolve. Okay, so this particular problem, that is the schema evolution thing, is majorly uh, happens with the semi-structured data. So let's suppose if you are having a JSON data, right, or if you are having some kind of let's suppose BSON data and all these kind of things, right? So where we are dealing with the semi-structured data. Sorry. So when we are dealing with the semi-structured data, schema evolution can be an issue. If we are working with event streams, event stream means when we are dealing with the streaming data. In that particular case, also schema evolution can be a challenge. As well as when we are working with the third-party sources, means let's suppose we are having any API using which we are ingesting our data, right? From the API, we are dumping that particular data into our data source, and then we are utilizing that particular data, right? So the API response can be changed anytime, right? Because it's not the headache of that particular organization which is giving the API response. It's our headache to adapt to whatever changes they make. They will not be informing us that okay, this is the, obviously if we have if we are using the enterprise version of those APIs, in that particular case there may be an agreement where the organization may have to inform you prior to doing any kind of schema change. But if we are going ahead with some kind of, let's suppose, free API and all those things, in that particular case there is no foundation on the organization uh, to inform the users of that particular API that okay, these are the schema changes we are making. So accordingly you can make your code changes. There is no such kind of uh, compulsion to the organization. Okay, so and what can happen is they may add new fields, means new columns can get added, right? Data type shift, maybe the data type of one or more columns can get changed. And nested structure evolve. So nested structure evolve means, so if you have seen our uh, JSON video, right? So how exactly JSON is? Okay. Not able to select. Pen is running perfectly fine. Right? I got it. Okay. So like how exactly this JSON file format is? So we have some key, right? Then we will have some value for this particular key, right? So it can be something like this, or maybe something like this. You can say we have a value, right? We will have value, and inside this value also we can have, let's say, key 2 and value 2. So this is a kind of nested JSON that we will be dealing with in that particular case, right? So here the nested data generally can change, right? The nested structure that will be inside here. So let's say we are having something as name, right? Let's say Vishal, right? Comma, age, let's say 27. Then we can have subjects, okay? And inside subjects we are having an array of value. Let's say subject 1, we are having English, okay? Subject 2, let's suppose computer science, and so on, okay? Something like this. So in the next semester, right, these subjects may get changed, right? So this structure will get changed. Maybe currently we are having 4 subjects. In the next semester we may have 6 subjects, right? So the schema of the nested structure will evolve, or it will get changed, right? So handling all these things is a complex task for the data engineers, okay? So how we will be able to involve it, how we will be able to solve the issue? Let's understand this thing, okay? So common changes in schema evolution include new column, additional fields not previously defined, sometimes with custom backfill value, okay? Means new fields is getting added, or a new column is getting added, which was not previously defined when creating the table, or when defining the schema. And these columns will have some kind of custom backfill values. Means the values of the like if it is getting newly added, but it will have the values of the columns of the rows that are already existing in the table, okay? Then column renaming. So changing the column name, for example, from name to full name. So column renaming also falls under schema evolution. Then dropping column, removing column from the table schema. It is also under schema evolution. Type widening, changing the columns type to a broader one. Means if we are changing the int, like currently we are having the data type as int, and we are changing that data type to double, that particular also, like this particular operation also falls under schema evaluation, which is I would say a sub part of type widening. Then other type changes. So changing a column's type, that is from int to string, okay? This also falls under our schema evolution process. So if you guys have gone through the delta table history video, right? So here what we did is, we first of all wrote our data frame into a delta table, correct? And after doing that, what we did is, we did some kind of transformation on our data frame. And what were those transformations? We first of all changed the column name, right? Then we performed some kind of filter operation, and then we added a new column, GDP per capita column we added, and like whose backfill value. So this is what we are backfilling with, right? We are giving a value of the new column, that okay, these will be the value of the new column, right? So this is what exactly backfilling is, okay? So what we did is, this GDP per capita incomes column values will be the GDP column divided by the population column of that particular row, okay? Then we tried to write this data again into the delta table that we had created earlier only. Right? We were not writing it to a new delta table. We are already writing it to an existing delta table. And here we received an error that a schema mismatch detected when writing to delta table. Okay. Moving forward, if you will read, to enable schema migration using data frame writer or data stream writer, please set dot option merge schema equals to true, which we ultimately did not did. We use the ddl command to change the schema. Okay, so ddl stands for uh, data definition language. Okay, so we used the ddl command to update the schema, and then once the schema got updated using the ddl sql query, we again uh, wrote the data frame, the transformed data frame into the same table that we were having, right? So this particular part we did manually. The schema management part was done by us manually. But if let's suppose we are dealing with the streaming data, right? Or let's say if we don't want to, like if we want to automate this schema management part, so how it can be done? Now we will be understanding that thing. Okay. So supporting schema evaluation is critical for building resilient, long-running pipeline that can accommodate changing data without frequent manual updates. Okay, so building such kind of pipeline or taking this schema evaluation into consideration while designing a pipeline will result that our pipeline will be resilient. Resilient means if any kind of schema change happens, like that pipeline will not fail. Okay, we will not have to let's say manually do the stuffs first of all, and it will not fail. It will try to adapt to that particular change, right? And it will keep on running. Okay, so if we want that we are designing a long running pipeline that we can use for a long time, we have to consider this schema change while designing the pipeline. Cool. Now let's understand what all components are there for the schema evolution part. So Databricks schema evolution involves 4 components, that is categories, 4 component categories, each handling schema evolution independently. Okay, so schema evolution involves majorly 4 components that are listed here, right? And each will handle the schema change independently. They will not, like they are not interdependent, or like one is not interconnected to another, right? Each will handle the schema change in an independent way that it will do. So connectors, first of all, so we already know what connectors are. So connectors are components that ingest data from external sources, right? Let's suppose we are having any external table, we are having any external volume. So we can use connectors, or maybe any external data source also, right? If we want to connect to some external database, to some external platforms like let's suppose Salesforce, Workday, right? And maybe our Google Analytics. So for connecting to all these platforms, we have our managed connectors that are already given to us by Databricks, right? So these include autoloaders, right? Kafka, Kinesis, Lakeflow, etc. Right? So we already have the managed connectors. So the first component will be connectors. Second components are format parser. So functions that decode raw formats including from JSON, from Avro, from XML, and from protobuf. Okay. So format parsers are nothing but these are the functions which decode the raw format of data, that which exact format of that particular data is, right? And it will be storing and managing that particular data in that format. What I mean with this particular thing is, so if I go back to my notebook and if I scroll to the JSON part where we will dealing with JSON data. We've written a lot of code in this particular playlist because we have covered nearly everything that is necessary in the Databricks domain. I won't say that we have covered everything in Spark, because Spark consists of much more things. Like we can also have this, what we call, the machine MLlib library, right? We also have graphics library, right? We have not covered those concepts because those concepts are not aligned to the data engineering part. Okay, so I guess this is the one, right? Yeah. So no, this is Memesis one. Is that JSON thing? So this is what we did, that we have created a function and using, yeah, here also we can do the same thing, right? Let's scroll down a bit. Okay. So here what we did, so you can see, right, that this is not a structured data, right? JSON belongs to a semi-structured data format, right? So when we are dealing or when we are storing the JSON file format, we are using this JSON, first of all, library, and we are using JSON.dumps, right, to dump the data into the particular table. Why? So that this schema formatter, right, like, or you can say this format parser, I would say this format parser can format or can parse this particular data in such a way that it will dump the JSON data into the table in a correct way. In a tabular form, it will dump, right? It will parse that, okay, this is the column name, right? These two are the column names and these are the values, right? Else it will not be able to, like, if we directly do it without using JSON.dumps, we have already seen that this thing, like we tried this thing without using JSON.dumps, we dumped the like the JSON format into table and we did not get the desired storage type that we wanted, right? But when we did JSON.dumps and inside JSON.dumps we passed the value of the JSON value, in that particular case the JSON was dumped into a correct format that we wanted, right? So these are what format parsers are, that for reading different kind of data types we will be using different format parsers. For JSON we are using from JSON Avro. If we want to deal with these binary file formats, we can use Avro. If we want to deal with XML, we can use XML. And if we want to deal with protobuf file format, we can go ahead with from protobuf. Then talking about the engines. So processing engines that execute queries including structured streaming. So these processing engines will also have their own schema evolution process that we will be for all these things we will be understanding what all schema evolution processes are there moving forward in the video itself. Then the data types. So streaming tables, materialized views, delta tables, and views persist and serve data. So we have already seen about all these data storages in the previous video itself, what exactly they are and how they are different from each other. We have already talked about it, right? So we will also see how these data storages will be able to, like, will themselves manage the schema evolution. Okay. If I talk about connectors, so we have connectors like autoloaders, Kafka, Kinesis, managed workflow, then format parsers. So we have format parsers like JSON, Avro, XML, and all these things. So these format parsers will be doing the schema management using the Kafka schema registry. Okay. It will be managing the schema using the Kafka schema registry. Then we have our processing engine, which so if you are dealing with the structured streaming, so if you are dealing with structured streaming, in that particular case schema evolution will require a restart, and why it will require a restart we will also discuss that particular thing. Okay. Then if we are dealing with the data sets, so data sets can be streaming table. So if we want to do the schema evolution in streaming table, we will have to like put this particular value as true. Merge schema value should be true, in that particular case, our streaming tables will be able to handle the schema changes. If we are dealing with materialized views, a full refresh will be required. Okay. If we are dealing with delta tables, again a a merge schema value should be equals to true. And if we are dealing with views, so there is something called as schema evolution or type schema evolution. Those things should be given. Okay. So what exactly? So this is just I would say a intro of these things. Now we will be understanding all these things in great detail. So for each component in data engineering architectures, schema evolution is independent. So you need to keep this particular thing in your mind, that all these components, it's not that if we have handled the schema change in connector, it will automatically handle the schema change in, let's suppose, my data sets. No, in connector we will have to handle the schema change separately or schema evolution separately, and in data sets I will have to, or maybe the data storage you can say, or data sets, whatever you want to say, we will have to manage them separately. Okay. You are responsible for configuring schema evolution in individual component to achieve the desired behavior in your data processing flow. So it will be our responsibility to configure each and every things in all the components where we require the schema evolution to be managed. Okay. It's not the responsibility of the Databricks or maybe the system that we are working in. For example, when using autoloader to ingest the data into delta table. Okay, so let's suppose we are having a condition where we are using connectors to load the data from some data source into our, let's say, delta table. Okay, so in this particular case there are two data storages. I won't say two data storages, two components, right? The first component is the connector and the second component is delta table. Okay, so now let's understand further. So for example, if you are using autoloader to ingest the data to delta table, there are two persisted schemas, right? So autoloader will have its own schema and the delta table will have its own schema. One is managed by autoloader, in which its schema location, right? And the other is the schema of the target delta table, correct? In a stable state, these two are the same. Okay, so in a stable state means when things are perfectly fine, right? When things are stable, in that particular case, the schema of my autoloader and the schema of my delta table will be similar, right? Now when autoloader evolves its schema based on the incoming data, the delta table must also evolve its schema or the query will fail. Okay, so again, as we have already talked about this, that these are two separate components. Autoloaders and the delta table are two separate components. So if autoloader evolves its schema based on the incoming data, my delta table will also have to evolve its schema based on the autoloader evolution. It's not that if autoloader has evolved its schema, delta table will automatically evolve it. No, we will have to configure the delta table separately for the schema evolution purpose, right? And if delta table will fail to evolve the schema, in that particular case our query, or you can say our pipeline, will fail. Okay, so what can we do in this particular case is, first of all, we can update the target delta table schema by enabling schema evolution or using direct DDL command. Okay, so to prevent our query to fail, the very first thing is what we can do is to enable the schema evolution by using this command, merge schema equals to true, right? Either we can do it or using the direct DDL command, which we did in the video, right? We manually did the schema evolution thing, right? If I come at the bottom, and if I scroll a bit more up, Here it is. So this was the manual process of doing the schema evolution, right? Which we used the DDL command to do the schema evolution. The second thing that, or the second option that is available to us, is do a full rewrite of the target delta table. That we can do a full rewrite operation on the target delta column. Means we will be, let's suppose, flushing out the old data and we will be rewriting the newer data into the delta table, right? Which is not, I would say, is a recommended process in this particular case. Now schema evolution support by connectors. Now we will understand one by one that these four components, what kind of schema evolution change will they support, right? The following section detail how each Databricks component handles different types of schema changes. First one is autoloader. So autoloader supports column changes but does not support type changes. Okay. So the autoloader component will only support the column changes. Let's suppose we have added a new column, renamed a new column, right? Or we have dropped a column. So all these changes will be supported by the autoloader schema change, or I would say the schema evolution engine. But the type changes. So let's suppose we have converted the int to double, or we have converted the string to int. In that particular case, it will fail, right? Let's read further. Configure automatic schema evolution with cloud files.schema evolution mode and rescued data column. Okay, so what exactly this rescued data column is, we will understand right now, right? And if we want to configure this schema evolution part, so from cloud files.schema evolution mode, we will have to set that particular configuration value. Okay, you can manually set schema hints or an immutable schema. When evolving the schema automatically, the stream initially fails. On restart, the evolved schema will be used. Okay, so when the schema evolution has happened, okay, like when the schema evolution has been happened automatically, the stream, if we are dealing with the streaming data, obviously if you are using the auto loader, in that particular case, mostly we will be dealing with the streaming data only, right? So in the first go, my stream will fail. I will have to restart the stream. Okay, I will have to rerun the code or restart the stream. And once after the restart, the evolved schema or the changed schema will take place. Okay, why this happens, we will further know in this particular video only. Okay, see how autoloader schema evolution works. So if you want to see how it exactly works, this is schema loader evolution, so you can go on to this link and you can read it in more detail. Now if talking about the what all schema changes is supported, so new column is supported depending on the schema evolution mode selected. Okay, failed with manual restart required to add new columns to schema. Okay, so there are different type of schema evolution mode. So depending on which type of schema evolution mode has been selected, it will support the new if new column is getting added, and the pipeline will initially fail and we will have to manually restart it to enforce the new schema change that has been done. Okay, then talking about column renaming, so this is also supported depending on the schema evolution mode selected. It will depend that if it will support or not. The renamed column is treated as a new column added and the old column is populated with null for new rows. Okay, fail with manual restart required to update the schema. So what this particular thing means is, so let's say earlier we are having a column named as name. Okay, let me reduce the thickness so that writing will be better. Okay, we have a column as name. Okay, okay, and we have changed the column name to full name. full name. Let's suppose like this. Okay. So in the previous like let's suppose before renaming, we will have some kind of data in this name column, right? We will have some data. Once this new column will be added, or basically when the column renaming will be done, it's not that it will rename this particular column, that it will change this particular column to full name. No, this will not happen. It will separately create a new column and it will start appending the data to this particular column, and it will add null values to the previous column that we were having. The name column we were having, it will not even drop it. It will start adding null values to the further rows that gets appended after the column name got changed, and a new column will be added as the whatever with the renamed column name that we had. Okay, so this is what it's saying, that the renamed column is treated as a new column added. The old column is populated with null values for new rows. Okay, I hope you guys understood this point. Then again, there will be a manual restart that will be required so that the schema evolution can be enforced, right? Then dropping columns, it's supported. It is treated as soft delete, where new rows from deleted columns are set to null. So if you are dropping any column, it's not that it will directly drop, it will delete that particular column. No, it will not happen. The column will be there. Okay, so let's suppose this is my column, right? We are having some values right here. Okay, so when this delete column will run, so what it will do, it will have the previous data, and the further data or the further rows will be replaced by null values. Okay, so here delete command ran. So now earlier data will persist and the newer data will be replaced by null values. Okay, so this is what soft delete is. Then type widening, as you are already aware about that, type change is not supported in the connectors, in the autoloaders. Okay, so type changes are captured in the rescued data column if rescued data column has been set and schema evolution is set to rescue. Okay, so if schema evolution mode is set to rescue and rescued data column is set, in that particular case type changes are captured. So you need to understand this, that it is only captured, it's not evolved. The schema will not change with the type, it will only capture that, okay, like the type of this particular column has been changed and now you need to do the change you need to do, otherwise requires a manual schema change. Okay, other type changes, again, if let's suppose int is getting changed to string, that is also not supported. Type changes are captured in the rescue data column if rescue data column has been set and schema evolution mode is set to rescue, otherwise requires a manual schema change. Okay, then talking about the delta connectors. So the delta connectors can support schema evolution if reading from delta table with column mapping and schema tracking location enabled. It supports schema evolution for column renaming, dropping column, and even the type changes. You can enable type widening with the type widening table property. You must set the correct Spark configuration for each of these respective changes to evolve the schema without stopping the stream. Okay, so if you are having, or if we want to enforce the schema evolution in delta connectors, so delta connectors first of all will support all kind of schema evolution, be it renaming a column, dropping a column, or even the type changes. Okay, if we want to enable the type widening, so there is a property of type widening in table that we will have to enable. Okay, by default it's disabled, and we will have to set correct Spark value, Spark configurations while running the Spark submit job. Okay, so that the schema changes can, the schema evolution or the schema changes can be captured and evolved automatically without even stopping the stream. So here the stream will not stop, right? We will not have to manually restart the stream. It will keep on processing and it will automatically detect and change it. Okay, if the configuration is not set properly, in that particular case we will, like, the stream the stream evolves its tracked schema whenever a change is detected and then stops. Okay. So if the configuration is not done, let's suppose, and what all configurations is there, we can see right here, right? And we will read about it. Okay. So if these configurations are not done correctly, or even if it is not done, in that particular case, the stream will track the schema change and it will stop. Then again, we will have to manually start the stream and resume the processing, right? Just like we did in the autoloader thing, right? But obviously, if we have the I would say the property of manual, like without manual intervention, we can keep on running the stream. So obviously, we should uh, we should configure the Spark in such a way that there is no kind of manual intervention that is required. Okay. Talking about the new columns. So new column is supported. The query fails and you must restart the stream to add a new column to the schema, but the delta table does not require a rewrite. Okay. So while adding a new column only, the stream will fail and we will have to manually restart the stream to add that new column schema change, right? But the delta table will not require a rewrite. So we will not have to rewrite the data after doing the schema change. Rest of the things can be done on the fly. Okay. Column renaming, it's supported. Can evolve schema within the streaming query with the Spark configuration. Spark.databricks.delta.streaming allow source column rename. Okay. So if we have set this particular configuration to true, it will automatically detect and will change the column name in the streaming itself. We will not have to manually stop, like it will not get stopped and we will have to manually restart it. The stream will keep on running and the column name will be renamed. Okay, so schema evolution will take place while the stream is ongoing. Okay, or you can say it will take place on the fly. Okay, then dropped columns, it's also supported. Can evolve schema within the streaming query with the Spark configuration. Spark.databricks.delta streaming allow source column drop. Okay, so if this configuration has been set, again dropping columns will be done on the fly itself. Type widening, it's supported. Can evolve schema within the streaming query with the Spark configuration. Spark.databricks.delta streaming allow source column type change. Okay, again if this is allowed, so type widening can be done in the streaming itself. We will not require any kind of manual restart. Other type changes, it's also supported, but requires a data table rewrite. Okay. For other type changes, means if we are changing the data type from int to let's say suppose a string, in that particular case it is supported, but in that particular case we will have to it will require a delta table rewrite, right? Without a rewrite, it will not be able to do the schema evolution. Can evolve the schema within a streaming query with the same configuration that was for the type widening itself, but the delta table rewrite will have to take place. Then talking about SaaS and CDC connectors. Okay, so SaaS, software as a service, right? And CDC means change data capture. Okay, so what CDC is, what exactly change data capture is, we will see in the very next video. So just bear this particular thing for a while. Okay, the SaaS and CDC connectors evolve the schema automatically when columns change. Okay, this is handled through an automatic restart when a change is detected. Type changes require a full refresh. Okay, so if we are having a SaaS connector or we are having a CDC connector, in that particular case, schema enforcement will be done automatically when the column will change. It will not require a manual restart. It will automatically restart when the change is detected. For type changes, a full refresh will be required. Okay, so talking about new columns, so it is supported. The query automatically restarts to resolve the schema mismatch. Okay, Column renaming, it is also supported. Query automatically restarts to resolve the schema mismatch. The renamed column is treated as a new column added. We have already talked about it, that how the renamed column will be treated as a new column. Dropped columns, so it is also supported. Dropped columns are treated as soft delete when new rows from the deleted columns are set to null. Again, we have already seen this particular part, and dropped columns are supported in our SAS and CDC connectors. Type widening is not supported, so updating the schema requires a full refresh. Other type changes not supported, updating the schema requires a full refresh. Okay, then if we are dealing with Kinesis, Kafka, PubSub or Pulsar connectors, majorly these connectors are the streaming connectors when we are dealing with the streaming data. So no native schema evolution is supported. Means Databricks native schema evolution support means these particular connectors themselves don't support any kind of schema evolution. Okay. Each of the connector functions return a binary blob. Schema evolution is handled by the format parser. Okay. So if you are dealing with any of these connectors, the schema evolution of like these connectors will not have any kind of schema evolution support inbuilt for them. So to handle the schema evolution while working with these connectors, we will have to do that particular thing with the format parser. Okay, so new column changes, it will be handled by format parser. Column renaming, again handled by format parser. Dropping columns, handled by format parser. Type wandering, handled by format parser, and other type changes handled by format parser itself. Then schema evolution support by format parser. Okay, now we will understand that what all schema evolution support format parser provides us. So again, we are aware about that there are different kind of format parsers. So first of all, we will get to know about from JSON parser. So the from JSON parser does not support schema evolution. Okay, you must update the schema manually when using JSON. When using from JSON format parser within a Lakeflow Spark declarative pipeline, automatic schema evolution will be enabled with schema location key and schema evolution mode. Okay, so even the from JSON parser does not support any kind of schema evolution. We will have to manually update the schema, right? If we are using the from JSON in the Lakeflow Spark declarative pipeline, in that particular case, automatic evolution, schema evolution can be enabled or handled by the schema evolution key and schema evolution mode that we were having in our autoloader component. Okay, so talking about new column, so when automatic schema evolution is enabled, it behaves like autoloader, right? So as we are already aware about it, that the autoloader component will be the one which will be responsible to track and to enable the schema evolution in from JSON parser. Then column renaming, when automatic schema evolution is enabled, it behaves like autoloader. Dropped columns, when schema evolution is enabled, it behaves like autoloader, right? Type widening, when schema evolution is enabled, it will behave like autoloader, and other type again, when automatic schema evolution is enabled, it will behave like an autoloader. Then the from Avro and from protobuf parsers. So the from Avro and from protobuf parser behave the same way. The schema can be fetched from Confluent schema registry. Okay, or the user can provide a schema and update the schema manually. Okay, so this Confluent schema registry is basically I would say schema registry that is provided us by the Confluent. Okay, so Confluent is basically an organization which provides us the managed service for Kafka. Okay, so if I talk about Databricks, so just like for schema management and all these stuffs, we are having the what we call this for schema management and the data governance part, we have in I forgot the name. Okay, it's Unity catalog. Okay. So we are having Unity catalog in Databricks. Similarly, for the schema management part in Confluent, we have the Confluent schema registry. So if I, okay, not here, or even I can open it here, or let's open in a new tab only. So here you will see that if your cluster has a schema registry service from Avro can work with, so that you don't need to specify the Avro schema manually. Okay, in the following example demonstrate reading a Kafka topic T, assuming the key and value are already registered in the schema registry as subjects T key and T value of type int and string. Okay, so what we are doing here is we are importing org.apache.spark.sql.avro.functions. So this is from like this particular code is in Scala, but we will be able to understand, right? Schema registry address we have provided our host and on which particular port it is running. Then we are creating a data frame. So spark.readstream format we are having Kafka. Options we are giving the servers right here, right? What we have to subscribe, so we have to subscribe to topic T dot load dot select. Then from Avro the data will be the key, right, the variable key, and subject will be T value. Schema registry address is schema registry address as key, and value will be the variable value will be T value. Again the schema registry address will be schema registry address as value. So we will have a column as key and value, where we will have in key columns we will have the topics key, and in the value column we will have the topics value, right? Key will be in string, sorry, key will be in int, and the string will be in the value will be in string. Okay, so there is no concept of schema evolution within the from Avro or from protobuf function. It will be handled by execution engine and schema registry. Okay, so new column supported by Confluent schema registry, otherwise user will have to update it manually, right? Column renaming supported by Confluent schema registry, otherwise manual update by user. Dropping columns Confluent supported by Confluent schema registry, otherwise the manual update has to be done. Type widening Confluent schema registry if supported, otherwise manual update. Other changes Confluent schema registry, otherwise manual changes needs to be done. Then the from CSV and from XML parsers, the from CSV and from XML parsers does not support the schema evolution. New columns not supported, column renaming not supported, dropped columns not supported, type widening not supported, and other type changes are not supported. Now schema evolution support by engines. Okay. So we have the processing engine in currently in Spark that we have is the structured streaming, right? The streaming queries schema is logged in during the planning phase. Okay, means on what schema, and this is exactly where you will get your question that why do we need a restart in case of when we will be enforcing the new schema. Why do we need a restart? Here you will get that answer. Okay, so a streaming query schema is logged in during the planning phase, and all micro batches reuse the plan without replanning, right? Means whatever stream of data we will be getting, the schema will be automatically, like the schema will be predefined without during the planning phase itself. Like when we are planning and when we are executing that particular stream, the schema will be automatically defined, and the Spark will create an execution plan according to that particular schema. Okay, if the source schema changes mid execution, the query fails. Okay, obviously because Spark has planned the execution plan based on the schema that we had provided during the planning phase, and if the schema changes, the query will fail. and the user must restart the streaming query so Spark can replan against the new schema, right? So this is your answer for the restart. That why do we have to restart? Because if we are restarting the Spark, or if we are restarting the stream, I would say, in that particular case, Spark will replan or re-execute the new schema that has been now enforced to that particular stream. Okay, and for that reason we have to restart our stream when we are trying to enforce the new schema on in that particular stream. I hope you got your answer. The data set that the stream writes to must also support schema evolution. Okay, new columns is supported. The query fails and you must restart the stream to resolve the schema mismatch, right? And why restart the stream? We are aware about it. Column renaming is supported. Query fails and you must restart the stream to resolve the schema mismatch. Dropped columns is supported. Query will fail and you have to restart the stream to resolve the schema mismatch. Type widening supported. Query fails, must restart stream to resolve the schema mismatch. Other changes is supported. Query will fail and you have to restart to resolve the schema mismatch. Then schema evolution by data sets. So what kind of schema evolutions? The data sets like the streaming table, views, materialized views, and delta tables will provide. Let's understand these things. Talking about the streaming table. So streaming table support merge schema evolution behavior by default. Updating the schema does not require a manual restart, but arbitrary schema changes requires a full refresh. So if there is some kind of updating the schema does not require a manual restart, means if you are updating, right? Let's suppose if we are just changing the column name, or we are adding a new column, dropping a new column, in that particular case, the manual restart will not be required. But if we are doing the type changes, in that particular case, a full refresh will be required. So new columns is supported. The query automatically restart to resolve the schema mismatch. Column rename is supported. Query restart to resolve the schema mismatch. Renamed column will be treated as a new column added. Dropped column supported. Dropped columns are treated as soft delete. Where new rows of the deleted column are set to null. Type widening is not supported. Updating the schema requires a full refresh. Okay. Other type changes not supported. Updating the schema requires a full refresh. Got it? The same thing is also mentioned here. Talking about the materialized view. So any update in the schema or the defining query triggers a full recompute of the materialized view is required. Means if any kind of schema change has been made to the materialized view, the materialized view will have to recompute it again. Means we will have to create the whole view basically again. So view, obviously we are already aware about the fact that it's just a virtual table, right? It is not a table where the actual data is getting stored, right? So if any kind of schema change is done on a materialized view, we will have to recompute, or you can say we will have to create that view again. Okay. So new column, full recompute triggered. Column renaming, full recompute triggered. Dropping columns, full recompute triggered. Type widening, full recompute triggered. Other type changes, full recompute is triggered. Then talking about the delta tables. So delta tables support a variety of configurations to update table schema, including renaming, dropping, and widening the type of columns without rewriting table data. Configurations supported include merge data evolution, column mapping, type widening, and overwrite scheme. Okay. So if I talk about the new columns, it is supported. Auto evolves when merge schema evolution is enabled without requiring a delta table rewrite. If merge data evolution is not enabled, update will fail. Okay. Renaming column is supported. Can rename through manual alter DDL command with column mapping enabled. does not require the table to be rewrite. Dropped columns is supported, can drop columns through manual alter table DDL commands with column mapping enabled, does not require a delta table rewrite. Type widening is also supported, handles certain types automatically when type widening and merge a schema evolution are enabled. You can widen column through a manual altered DDL command when type widening is enabled. Without either configured, operation will fail. Okay. Sorry. Okay. So if we are going ahead with the type widening thing, so type widening is supported, but certain types of type widening is supported automatically. If we want to do any kind of type widening that is not automatically supported, in that case we can also do the manual alter table DDL command to enable the type widening. Okay. Other type changes is also supported but requires a full rewrite of the delta table. You must enable overwrite schema, which enables the full rewrite of the delta table, otherwise operation will fail. So if we are doing some kind of other type changes, right, in that particular case we will have to enable this property, that is overwrite schema, otherwise the full rewrite of the delta table will not happen and our operation or our pipeline will fail. Then talking about views. So if a view has a column underscore list that does not match the new schema, okay, or it has a query that can't be passed, the view becomes invalid. Okay. So there is a property that is column underscore list. If it will not match the new schema, okay, if it will not match the new schema or the query will not be able to parse it, in that particular case the view will become invalid. Means we will not be able to query that particular view. Basically it will become corrupt. If it does not, you can enable the schema evolution for type changes with schema type evolution, and for type changes as well as new, renamed and dropped columns with schema evolution. Okay, which is a superset of schema evolution. Okay, so superset means under this schema evolution itself, this schema type evolution belongs. So if this new columns is supported in views, so with schema evolution mode, the view auto evolves without any kind of manual intervention if there is no explicit column list that is defined. Otherwise, the view will become invalid and the user cannot query it. Okay. So if this column underscore list is defined explicitly, in that particular case, this schema evolution mode will not work, and if any kind of schema changes happen, the query will become invalid and the user will not be able to query it. If there is no explicit column underscore list is defined, in that particular case, this schema evolution mode can come into picture and it will auto evolve according to the schema and no manual intervention will be required. Similarly, column renaming is also supported. So with schema evolution mode, the view auto evolves without any manual intervention if there is no explicit column list. Otherwise, view will become invalid. Same thing as new columns. Dropped column will have again the same thing, supported schema with schema evolution mode. The view auto evolves without any manual intervention if there is no explicit data column underscore list. Otherwise, the view becomes invalid. Then there is something called as type widening. So it is supported with schema type evolution mode. Okay, and we are aware about this fact that schema this is a subset. Schema type evolution is a subset of schema evolution. Evolution mode, the view auto evolves for the type changes. With schema evolution mode, the view auto evolves without any manual intervention if there is no explicit column defined. Otherwise, the view will become invalid. For other type changes supported, it's also supported also with type evolution mode. The view auto evolves for any changes. Again, schema evolution mode will automatically evolve without any manual intervention if this column underscore list is not explicitly defined. If it is defined, the view will become invalid. Okay. Now let's understand an example. The following example shows how to ingest a Kafka topic with Avro encoded payload registered with Confluent schema registry and write them to a managed delta table with schema evolution enabled. Okay. So what I will do, okay, I will explain this particular code to you guys currently. But what I am thinking is I will also create a detailed Kafka video, right, where we will be understanding all these concepts, the architecture of Kafka, what exactly this Kafka topic is, right, what exactly Kafka broker is, right, what are consumers, what are producers, what is the schema registry, and all those stuffs we will be covering in that particular video, right, and then I will be showing you the demo, practical demo of this particular code, so that you guys can have a better understanding of what exactly is going on this code. I can explain you manually for right now, right? And I will be for sure covering a detailed video for Kafka. Okay. Key points illustrated. So we will integrate first of all the Kafka connector. Then we will decode the Avro record using from Avro with the schema registry. Then we will handle the schema evolution by setting Avro schema evolution mode. Then we will write the delta table to merge schema enabled and allow additive changes, right? So let's understand the code and let's see what exactly we have to do, right? So first of all, we will have to define a catalog and a schema. We already know. Then we will have to set up the Kafka thing, right? So these all things are the Kafka setup. So we will have to first of all set the schema registry. We will have to give the schema registry endpoint. We will have to give the user name, the user password, right? Bootstrap on which IP this the Kafka server is running, and the topic name from where we will ingest the data to the delta table, basically the streaming delta table. Then we will create a bronze table. Basically, we will create a table in the catalog.schema and the table is named as bronze underscore users. For checkpointing, we will create a volume in volumes / catalog / schema checkpoints bronze underscore users. Then we will have to authenticate, right? So using this code, and here we will have to put our username and password, okay, which we have already defined here in the configuration, right? And then now the code comes into picture. First of all, we will do the required imports. So we will import column and we will import from Avro from pyspark.sql.avro.functions. Then we will build a reader. So from spark.readstream format will be Kafka, right? The servers will be these, right? Here we will define the server, right? That this is the point where my Kafka server is running. Then what you have to subscribe, which topic you have to subscribe, we have already defined it here in the configuration, right? And we will set an option that is starting offsets is earliest. Then we have to attach the Kafka authentication. So for key value in Kafka ops.items, right? Reader.option, and we will put this key value in the reader, and we will load this reader variable into a raw df. Okay. Now what we will do is we will decode this. Decode this particular data frame. So from Avro, data will be the column value, JSON file format will be none, subject will be topic hyphen value, schema registry we have already defined on the top. Then we have a few options that we have to put here, and we will rename that particular thing as payload. Okay. And then we will create a new data frame bronze underscore df, where we will select from raw df, we will select the decoded as a timestamp, right? And we will select payloads all column, and we will add the timestamp here. And then we will be writing this bronze underscore data frame to a streaming delta table. So bronze.df write stream, the format will be delta. Okay. The checkpoint volume we have already created. So this is the checkpoint location. ignore changes true, append, the output mode is append, and here if you check, so we have given merge schema equals to true, so it will automatically support new column renaming and all those things will be handled. Trigger available now, and to table where the bronze table that we had already given, catalog slash schema slash bronze table, we had already created this particular table on the top. Okay, so it will start storing the data from the stream that we will get from this particular topic, right? So this is how basically the schema evolution is enforced during the code. Okay, so this is a whole ETL pipeline that we have written, right? Basically not we have written, the developers has given us as an example, I would say, right? And this is how the schema evolution has been captured and managed by them. Cool. So need not worry if you are not aware about what is this bootstrap is, what Kafka topic is, right? What schema registry and all those things is. I will be creating a separate and detailed video about Kafka very soon. Cool. So I hope you guys learned something new in this particular video. I will see you in the next one. Till then, keep learning and keep growing. Bye bye.